Search systems waste work checking items they have already seen. A Bloom filter gives fast duplicate checks with a controlled false positive trade-off. You'll learn how the pieces fit into a workflow that remembers seen items and skips repeated lookups with visible risk. I'm Professor Pi, teaching AI foundations with simple Python. Search engines and indexers often touch the same document or term over and over. That repeats CPU work and raises latency whenever your pipeline queries a slow index or an external service. A Bloom filter helps by asking a cheap question first. Is this item definitely new, or could it already be indexed? If the filter says definitely new, you can skip expensive negative checks. If it says possibly present, you fall back to an exact check. When most queries are repeats, that trade saves a lot of time. At a high level, a Bloom filter stores a compact fingerprint instead of full items. It's just a small bitmap where several hash functions flip bits for each item. You don't keep the string itself, so absence is guaranteed, but presence is only maybe due to collisions. The upside is tiny memory use. The downside is false positives, which in indexing usually just cost an extra exact check rather than causing data loss. We'll walk a tiny demo pipeline in 5 steps. First, an exact set baseline. Then, hashing words to bit positions. Then, a working Bloom filter. Then, measuring false positives. And finally, putting the filter in front of an index to save lookups. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. That clear baseline leads us into the first piece, the exact duplicate check against a small stream. This snippet implements the smallest exact duplicate check for a tiny document stream. Search pipelines often see the same item more than once, and an exact set is the easiest way to prove what should be kept. The code walks through docs, stores each new document in scene, and appends only first-time documents to unique. This is memory safe and has no false positives, but it can grow large when the stream is huge. The output shows how many documents remain and how many repeated items were skipped. Now that we can detect true duplicates exactly, we need a compact way to represent terms as positions instead of full strings. This example turns a word into multiple bit positions, which is the core move behind a Bloom filter. Instead of storing the whole string, positions gives a few indexes inside a fixed size bit array. The small size equals 16 keeps the idea visible on screen, and the 3 seeds act like 3 simple hash views of the same term. This teaching hash is intentionally compact. Production filters usually use stronger, well-distributed hashing. The output shows exactly which bit positions cat would touch before we store anything. With bit positions identified, the next step is to build the bit array and mark positions for every term we want to remember. This code builds the first working Bloom filter state from the unique documents. Each word is split out of each document. Positions maps that word to several indexes, and bitspos equals 1 marks those locations as occupied. A query checks whether all of its positions are already set, which means the term is possibly present. If any position is 0, the term is definitely absent. The output shows that the filter recognizes cat as a possible index term, which is enough to avoid some unnecessary negative lookups later. Now we should make the trade-off visible by comparing the Bloom output against the exact ground truth. This snippet compares the Bloom filter against an exact set, so the trade-off becomes visible. Indexed is the ground truth from the documents, while tests includes words that are both present and absent. False hits collects absent words that still pass the Bloom check because their bit positions happen to be set by other words. That is the key Bloom filter limitation. It can say possibly present for a missing item, but it should not say definitely absent for an inserted item. The output shows a measured false positive rate on this tiny test batch. Finally, we wire the filter into a simple indexing stream so we can count how many exact index lookups we avoid. This example uses the Bloom filter as a small lookup gate for an indexing stream. The safe pattern is important. When maybe is false, the term is definitely new, so the code can skip the exact index check. When maybe is true, the code still checks index, because a false positive should not cause a real new term to be dropped. New terms are added to index, recorded and added, and written back into bits so later queries can see them. The output shows saved exact lookups and the terms added to the baseline index. In a real search system, you would map documents to terms using the same tokenizer and then use a larger bit array and stronger hashes. Using this filter in front of a slow exact index lowers throughput costs and reduces load spikes when repeated items dominate traffic. A Bloom filter in one line, a compact probabilistic set that answers definitely not or maybe yes for membership. Use it as a fast pre-check to avoid expensive negative index lookups on repeat traffic. One important caveat: false positives can occur, so never use a Bloom filter as the only authority when you must not miss a real new item. To extend this demo, tune the bit array size and the number of hash functions, and measure the false positive rate on your actual corpus. For example, the live query logs you plan to index. That one change will show the memory versus extra check trade-off clearly. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.